Well, hello, this is my contribution to 6F. We've been talking a lot about Euler over the last few weeks. Now we're going to introduce another gentleman, Hamilton, and these two gentlemen had completely different approaches to analyzing graphs and working out how best to use them. The issue is finding the best way to get around a delivery service, for instance. I've got on the screen a map of Canberra with a number of major centres marked on it, and obviously there are ways of connecting them. Now notice that I'm not joining up by going down the roads, I'm just joining up nodes, which you can do. Question is, given all these connections, what is the best way to get around the network in terms of saving time? If you've got a delivery service, you don't want to be going to multiple places in order to get around everywhere, nor do you want to be going over all the roads more than once. So that's the issue that is being discussed by these two gentlemen. There's Euler on the left, Hamilton, who was a Scot, is on the right. First of all, we need to just have a quick review of traversable graphs. If you remember, this is where you can put your pen down somewhere, one of the nodes, and trace around all the other points and cover all the paths. Now, that's Euler. If we are going to traverse the graph that you can see on the screen, we need to be able to go over all the edges of the network once and once only. A reminder of what a traversable graph is on the right there. It's a trail, and a trail is a walk with no repeated edges. So it's a trail that includes every edge once and once only. The one on the screen has got no odd nodes. A is 2, B is 4, C is 4, D is 2, and E is 4. So this one is traceable, as you should remember, in that you finish where you start. Just check that works. So anywhere, it doesn't matter where you go, it doesn't matter how you do it, you will always be able to finish up where you start. Now, that is now to be called an Eulerian graph. If it wasn't already, we're now definitely calling that an Eulerian graph, which is to be distinguished from the next one, which is another traversable graph, but this time, this one's got two odd nodes. There is an odd node and there is an odd node. The other one is even. And in this case, if you want to traverse it, you start at one place and finish at the other. We've done all that already, so we can go starting at A, go down to C, back up to A, over to B, and finish down at C. The name for this is now a semi-Eulerian trail. So that's the two kinds of traversable graph. And Euler, as we've said before, is dealing with edges. E for edges, E for Euler. And just for the record, here's another one that is not traversable. It has got 1, 2, 3, 4 odd nodes, which is why it's not traversable, so that doesn't come into any consideration here. This is a summary of what I've just been saying so far. So we have an Eulerian graph, if you remember. Apart from the fact that it has to be connected, all vertices even and start at any vertex and finish at the same one. A semi-Eulerian graph is one where it still has to be connected, but it's got exactly two odd nodes, and it will start at one and finish with the other. Hamilton didn't concentrate on edges, he concentrated on vertices. As long as you go to every vertex, that's good. Now, so thinking back to that drawing I had at the beginning, we have a map. Maybe sometimes it's requirement of the delivery service to go to along every road, especially if you're doing lots of deliveries on the way. Hamilton was looking at just going to every place once and once only. So on the screen we've got a diagram of A, B, C and D. We haven't crossed every road in order to get through every town. We went from A to B and then from there to D and then to C, and there's multiple other ways of doing it. But that is a Hamiltonian path if you can visit one vertex each only. Hamiltonian cycle, which makes sense if you think about it, is if you have a delivery service, you want to finish up at home after you've been everywhere. So in this one, starting at A, going down to C, then down to F, across to E, up to D, up to B. You've been to each town once only, but you finished up at home. That's the Hamiltonian cycle. And there's the summary of that. Hamiltonian path visits every vertex of a graph, but doesn't necessarily get back home. Hamiltonian cycle starts and finishes at the same place. So that's basically what 6F is all about. Let's have a look at this example here. This is a map that's out of the textbook showing a few towns down in Victoria, St Andrews, Kinglake, Yarra Glen, Toolangi and Healesville. And they're saying draw a graph with a vertex representing each of those 5 towns, edges representing the direct road connections between the towns. Now, okay, I could draw on here, there's lots of roads and others, but that's not quite what the circuit is going to look like, because we have a town there and a town there, the 5 that they're mentioning. But we don't need to join them up with those lines. We need to actually join them up like I'm going to do here. So we want to go down to there. There's a connection between Kinglake and Yarra Glen. There's a connection between Kinglake and St Andrews. St Andrews and Yarra Glen. Kinglake and Toolangi. Toolangi and Yarra Glen. Toolangi and Healesville and Yarra Glen. So that's not really following the roads, that's just showing the connections between those nodes. My next slide is pretty similar, I did that before. Alright, so we've done part A, draw a graph with a vertex representing each of these towns and edges, representing the direct road connections. Explain why the graph is semi-Eulerian, but not Eulerian. Well, can you remember that a semi-Eulerian has got 2 odd nodes, which is Kinglake and Toolangi, the others are even. So that's that done. To write an Eulerian trail that begins at Toolangi, remember we've got to cross every edge, every road. So starting at Toolangi, I might go down to Healesville, cross to Yarra Glen, back up to Toolangi, across to Kinglake, down to Yarra Glen, up to St Andrews, and then the last step is Kinglake. That's that done. And a Hamiltonian cycle beginning at Healesville, which is here. So we're going to go starting at Healesville. Got to finish up at Healesville, we can just go around the outside. We've been to every town and got back where we started. Now, there's quite a long exercise, 6F, pages 233 to 6. I seriously encourage you to work your way methodically through all those questions, at least some of each of questions 1 to 9 or whatever it is, so that by the time you've finished, the concepts in this exercise will be embedded. So that's your success criteria. I can distinguish and identify Eulerian graphs and Hamiltonian paths and cycles. Thank you.